Hey, good afternoon, everyone. So, integrating Vulkan ray tracing in Godot. How cool is that? So, who am I? My name is Antonio, and I'm a software engineer, and I'm based in Italy. 9 years ago, I moved to the UK, and where I started my career in the graphics industry. I worked for Imagination Technologies, ARM, Collabora, Qualcomm, and now I've been working at LunarG for more than 1 year. I also play the piano. I like computer games, board games, fantasy, science fiction, and of course 42 is my favorite number, if you know what I mean. I also like computer graphics and I like learning new stuff. So during the pandemic, I went deep on learning ray tracing. So I wrote a software renderer from scratch. I implemented a path tracer. I learned new interesting techniques like importance sampling and multiple importance sampling. So I was able to render really cool images like this Stanford dragon here. And why ray tracing? Well, with ray tracing, you can render really awesome pictures, right? With ray tracing, you can simulate the physics of light accurately, so you can get really nice, cool, interesting effects like better shadows and global illuminations, reflections and refractions. I'm not the author of the picture on the right. I got this from Wikipedia, but I am the author of the picture on the left. So at a certain point, I wanted to share this with more people, but my code was just a prototype and nobody would care about my prototype. So this is where Godot comes in. I don't know if you are aware what that is. This is a game engine, and a lot of friends and colleagues use it. It's a great platform, and for me, it ticks many boxes. Like it's popular, it's open source under the MIT license, it's multi-platform, it doesn't require to pay any royalties for publishing your game, and it's just a file that you put in your desktop, you double-click and boom, it works. But more importantly, it compiles in a few minutes on my machine, which you know what it means if you've compiled other game engines in terms of productivity. But a couple of years ago, it had no support for hardware ray tracing, and so I thought, well, I could help with that. So how cool would it be to have something like this in Godot? So what you're looking at, this is a technique called ray traced ambient occlusion, which is basically trying to guess where the light struggles to reach. For example, you can have nice soft shadows below the cube there. You can see behind the curtains, for example. This is an area where the light has very difficulties to reach. Okay, so adding Vulkan ray tracing to Godot. How hard could it be? This was the challenge. I have this bunch of Vulkan code in my prototype, which is basically the result of following the NVIDIA ray tracing tutorial. And you know, you can't just take this code and put in Godot. It just doesn't work like that. So, but by the way, you need to basically do 4 main things. You need to create a bounding volume hierarchy, then you need to create a ray tracing pipeline, then you need to create a shader binding table, and then you can trace. I'll go in a bit more details in each of these things, so let's start with the bounding volume hierarchy. What is it? Okay, so this is basically boxes containing geometries. And what problem does it solve? Well, you can imagine that when you want to ray trace something, you need to shoot the ray, and then you need to look for an intersection. So in your scene, you might have many geometries, and you need to iterate through all of your geometries and look for an intersection with your ray, and that basically is just a linear algorithm, and it doesn't scale nicely. If you have a scene with many geometries, you basically need to check for an intersection for all the geometries. So what you can do, you can actually subdivide the space, for example, and you check for intersection on each cell of your space. And if you hit the cell, then you can go down and look for the geometries in your cell. So basically, the algorithm at this point becomes logarithmic. Okay, and then we can also subdivide the space within the space. So we can create a top-level bounding volume hierarchy at the top, and then we can create a bottom-level acceleration structure, bottom-level bounding volume within the top-level bounding volume. All right, so in terms of pseudocode, you can see you can basically iterate through all the pixels in your frame buffer. You generate an array and you look for an intersection by traversing the bounding volume hierarchy. And you get either you get an index of your geometry, or you don't hit anything. The array doesn't hit anything, so you have a miss. You're missing all the geometries. But if you have a geometry, then you can shade. You get the material corresponding to the geometry, and then you, according to the lighting model, you get a pixel color onto the screen. What is a ray tracing pipeline? Okay, this is an interesting thing. It's basically tied to the GPU, the graphics processing unit. And there are hardware modules for that. So I'll keep it simple. As I said, you generate an array, and then you can trace this by looking for intersection into the bounding volume hierarchy. And within the GPU, this is a data structure, and it is accelerated by the GPU. That's why we call it acceleration structure. So it's doing the traversal, and we are looking for an intersection. And if we have an intersection, we need to ask, is this the closest geometry to the origin of the array? If so, we have a closest hit, and we need to define a shader for that, so we get the color. Otherwise, if we have no hit, we have a miss. We're missing all the geometries, but we still want to do something. For example, we want a color for the sky. In this case, we can use the miss shader. And all the colored boxes, these are shaders that we can define. And I'll mention these later in a few slides. Okay, so I have this Vulkan code. I want to put it in Godot, but it cannot put it just like that. I shouldn't break the engine, first of all, and then it should fit the Godot rendering abstractions. It should do automatic synchronization via the render graph. I'll mention what that is. I need to expose this new ray tracing API to the user via scripting, and then it should be multi-backend friendly, because we don't have just Vulkan, we also have DirectX 12, and we have Metal, so this should be a unified interface. Okay? So what is the end goal? Brace yourself. I'm going to show you some code. This is the end result. Imagine this is just very simple idea of what the code should look like. If you're familiar with GDScript, you're familiar with the RenderingDevice object, you probably already used that at the very top. But these functions in yellow, these are new functions available to you. You can create the top-level acceleration structure, you can create a bottom-level acceleration structure for the geometries in the scene, and then once you have that, you can issue commands to the GPU by binding the ray tracing pipeline and by binding your objects by pushing them into the GPU, and then you can trace ray, which is the most important thing, I guess. So, but where does GPU rendering live in the engine? What do I mean by that? Where is the code? What code should I touch? So I came up with these. There are a bunch of classes in the Godot source code, which are the RenderingDevice, the RenderingDevice graph, and the RenderingDevice driver. The RenderingDevice driver is a polymorphic type. This is an abstraction. It's a unified interface over the graphics APIs available to us. So there are concrete implementation of this class for Vulkan, DirectX 12, and Metal. Somewhere in the middle, we have the RenderingDevice graph. I really love this class. This is the authority on synchronization. It's responsible for recording commands, and it's responsible for tracking resource usages. What are resource usages? I'll mention them later. And then it's generating barriers according to resource usages, which is so useful to me. And then it submits commands to the driver. But what are barriers? Well, you can imagine that The GPU is a highly parallel hardware. So it tries to do everything at once if it can. It has so many cores that it tries to do everything together. But sometimes you don't want to do this. You just want to do something first, then something after that, and then you need to wait to tell the GPU, please, wait for this operation to finish before starting the next operation. And this is a GPU barrier. Just telling this, do these commands, then wait for this command to finish, and start the next commands. And I don't need to issue them myself. The barriers are generated by the RenderingDevice graph. That's why I like this class. So how does it work? So it works by creating a data structure which is a direct acyclic graph, which is basically a bunch of nodes, and all the nodes represent a GPU operation. GPU operations like pushing a data onto a buffer into the GPU, or doing a render pass, or doing a compute pass. And the edges among the nodes are resource usages. And so basically, resource usages are things like, do I read from the resource? Do I write onto the resource? Do I use it for a specific reason? So with this information, the RenderingDevice graph is able to detect the right dependencies between the operation and the resources, and it generates barriers for me. So there is a really nice blog post on Godot Engine, a website written by Dario Banini, which is called GPU Synchronization in Godot 4.3 is Getting a Major Upgrade. So if you want to get a better understanding of the topic, I'll definitely recommend reading that. And then at the very top, we have the RenderingDevice. This is the GPU API. This is the thing that it's exposing the rendering API to you Godot developers. So it's responsible from this perspective for anything. It's responsible for creating GPU resources and for recording commands. And it's doing that by delegating all of this to the other classes on the right. Anything that involves command recording and synchronization goes to the RenderingDevice graph. Anything else that it needs resource managing goes through the RenderingDevice driver. Okay, so the idea is to do the ray tracing hello world, which is, in my mind, one triangle and shooting one ray for each pixel of the frame buffer. So what does it take? And what is the minimum set of changes needed to get a ray traced triangle on the screen? Here's the roadmap. This is what I ended up doing. There is a nice bar at the bottom that you can follow. So just while I guide you through the implementation process, you don't get lost in the meanwhile. So I'll start with extensions and properties. I'll introduce new types, new API available to you. I'll mention acceleration structures, ray tracing shaders, and then recording commands. Let's go. Okay, Vulkan requirements. So not every GPU has ray tracing capabilities. These features are quite new in the industry. So in Vulkan, the ray tracing API is an extension. So that means that it's not enabled by default. So I need to query the GPU. It's basically asking, do you support acceleration structure? Do you support ray tracing pipeline? Do you have all the requirements I need for my API? So if that's the case, then these new Godot API, these capabilities will be available to you. Otherwise, it won't. And then there are some properties that I need to query to the GPU, properties for the size of objects, right alignments in memory. This is something that you probably won't care, and I'll take care of this, so don't worry about that. We have a new pipeline type. So far we have a rasterization for drawing something on the screen. We have the compute pipeline for doing generic computation. We now have a new pipeline for doing ray tracing. That's so cool. Okay, so together with the pipeline, we have new shader stages. The raygen shader, the miss shader, the closest hit shader, and intersection shader. We need to specify how we generate rays. This is important. And generally, we generate rays where the camera is, and we shoot a ray towards the direction of the camera. And then we have the miss shader. What happens when we don't hit any geometry? Maybe we want the color of the sky. Then we need to specify the closest hit shader. What happens when we hit the geometry and the geometry is the closest one? And then we have the any hit shader, which is called every time the ray hits something. And this something doesn't require to be the first thing closer to the origin of the ray. So it might be useful for transparency. And then we have the intersection shader. If we don't define this, the GPU is just working with triangles, and it has the hardware module for accelerating intersection between the ray and the triangle, so it's super fast. But we might want to specify different geometries. We might have our mathematical model for our geometries. For example, we might use the intersection shader for signed distance function, and I think that would be so cool. And I create shader stages. I group them closest and any hit shaders, and together they form a ray tracing pipeline. Okay, at this point I have a question, which is where do I put my objects? I have these objects I created with Vulkan code. I need to store them somewhere. I need to specify their lifetime, who creates them, who destroys these resources. And there is these nice things in the Godot source code, which is the concept of owner. This is an object which holds all these GPU resources, basically, and you put these objects into the owner, and the owner gives you a lightweight ID, which is the RID. And this is just an access key that we can use to get the object back from the owner. So I ended up creating an owner for the acceleration structures and the owner for the ray tracing pipeline. At this point, we have new engine APIs. So these are a bunch of functions available to you by the RenderingDevice class, and this is definitely what you care about, but it's still experimental. What does it mean? It means that the name of the functions might change in the future, the parameters might change in the future as well, but so far we have functions for creating a BLAS, a TLAS, and for building them, and for creating the ray tracing pipeline. We also have commands for recording, functions for recording commands. We'll show you later. The instances buffer, this is a really interesting object. It's basically a way to build the bounding varium hierarchy. In order to build a BLAS, we just need a collection of geometries, and we put the geometries into the BLAS. For the TLAS, this is different, because we cannot just put a BLAS into a TLAS. We might want to use the same BLAS, and we might want to instantiate multiple times and move it into space. So this is done via the instances buffer, and this is just getting a reference to a BLAS and a transform 3D so we can move it into space. The scratch buffer, this is needed when we build acceleration structures. That's just the GPU telling us, hey, I need some memory where I do some computation when building the acceleration structure. And you should give me that. And I say, well, why? Can you figure it out yourself? And basically, no. So I just need to specify this to the GPU, and then the GPU is able to build acceleration structures. You won't ever care about that. I'll take care for you. And then we have acceleration structure usages. I mentioned when talking about the RenderingDevice graph that we have operations and we have resource usages. In this case, the operations are building acceleration structures and tracing rays. When we build an acceleration structure, we might want to read from the acceleration, or we might want to write in order to build it. If we are building a TLAS, we want to use the BLAS as a build input, and when we trace rays, we might want to read from the memory which represents the TLAS. From these things, the RenderingDevice graph is able to generate Vulkan barriers for me. That's so cool. Ray tracing shaders, okay, this is the part where I introduced new markers in source files. We have markers for raygen, miss, closest hit, any hit, and intersection. And here we have an example. You can imagine this is just one source file, And we have three shaders: the raygen shader, the mist shader, and the closest hit shader. The raygen shader on the left, I'll tell you what it does. It's just generating a ray at the origin, and the direction is towards the z-axis. And there's also probably some bug somewhere there. Then we have the mist shader. What happens when we don't hit anything? This is just going to return a red color. And we have the closest hit shader, which is going to return a green color when we hit actually something. Okay, the shader binding table, this was a headache for me. So the thing is that this is an object that the GPU wants when you build your shader in your pipeline. And it's not just, it doesn't contain just shaders. It doesn't contain just shader handles. It contains a shader group handles. And what are those? I don't know. I mean, it's the way to group shaders together. But when I build these, I also should take care of the size of the handles, the alignment in memory, and the strides of the region. It's really complicated stuff that you would never care. So let's go ahead. Command list, this is the way that Godot records commands, and they put commands into a list. So we have a draw list for the rasterization pipeline. We have a compute list for the compute pipeline. We now have a ray tracing list for the ray tracing pipeline. What does that mean? It's just a bunch of new functions in the rendering device, and these are available to you via GDScript. We have functions for starting to record. So we have a ray tracing list begin and ray tracing list end. In the middle of these two functions, we should bind objects to the GPU, we can push data to the GPU, and we can also trace rays. All right, so we're going back to our minimal sample, this time with more details. At the very top, we still have the rendering device, but we can query the rendering device. Do you support ray tracing pipeline? And then the rendering device will say yes. In this case, we have all these nice functions available to us. We have a function for creating the BLAS, and when we create the BLAS, we specify a collection of geometries from the scene, possibly, and the geometries in this case are opaque. They might also be transparent, for example. And then we can define a TLAS. In this case, I'm creating a TLAS with just one instance. In this instance, I'm going to put my BLAS at the top. And with this, I create a BLAS. At this point, I don't need to do any synchronization because Godot is doing synchronization for me. So I start immediately recording commands for the ray tracing list. So I call the ray tracing list begin, and then I can bind the ray tracing pipeline, and then I can bind the uniform set, which is data I push to the GPU, and then I can trace rays. And once I'm done, I just need to stop recording by calling ray tracing list end. So a bit about this ray tracing pipeline object. How do I create these? It's super easy. You have a GLSL shader, and you load this shader, and you compile this into an intermediate representation for Vulkan, and then you create a shader object from the sphere V. You put this together into a pipeline shader, and you group them for the hit group, and then you create a ray tracing pipeline. It looks convoluted, but I guess you'll figure it out. And then when we need to create uniforms, this is just how we push data to the GPU. In this case, we have, in my sample, I have two uniforms, one for the output image and one for the TLAS, which is the object I use in order to traverse the hierarchy, in order to look for intersections. And here we have our nice triangle. You can see the triangle is green, meaning that the ray hits a geometry, and red means that we have a miss. The ray doesn't find anything it doesn't intersect anything. And this is the PR. So basically, at this point, I had enough code for me to say, this is enough. I don't want to do more stuff. I want to create a pull request with this, and I want it to be just the minimum set of changes possible for implement this feature. Otherwise, it would be difficult for Godot developers to review the code, and it would be difficult for me to iterate over it. Still, it's 3,000 lines of code, and there are 174 comments, mostly asking for changes. And I opened this in the November 12, 2024. And it was merged in January 27, so a few months ago. And I want to say thank you to the reviewer on the right. Kalinu, Mikeon, 1000 Chips, Dario Samo, Caggiano, and Zux. Thank you very much for reviewing my code. But on another branch, which is not going to be a pull request, I went ahead because I wanted to get the geometry from the scene and forward this geometry to the ray tracing pipeline. So I was able to do this. And this is Sponza, but it's half Sponza. There are some geometries that are missing. I was asking, where have these geometries gone? Why I can see some geometries and some geometries are not there? I needed to debug this. And then I noticed this weird cube in the middle of the scene, and it's really weird. It's just not a cube. There are some things in it. So I opened this in a profiler, and I noticed there were indeed many geometries in here, and the vertex positions were between 0 and 1. So I know I scratched my head. Maybe there is some compression going on here. Indeed, Godot, it's compressing vertex attributes when you import a model. So I just needed to disable this behavior without compressing vertex attributes, and boom, I have my Sponza nicely rendered via the ray tracing pipeline. So I was so happy. And in this screenshot, you can see again ray trace the ambient occlusion, and I noticed that there is a nice node in Godot, which is the world environment node. I realized, well, I could use this node to add a post-processing step to Godot, and I could use it to ray trace the ambient occlusion, and then put this together with the default forward plus pipeline with the default color. So this is how the forward plus pipeline looks like without ray tracing ambient occlusion. This is just normal. And this is with ray tracing and ambient occlusion. So cool. Look at the difference. Especially below the cube, you see this nice soft shadow, and behind the curtains, you now see these dark areas where the light struggles to reach, and it's so nice, I believe. What is next? Well, with this, I guess we can do something cool like ray trace the reflections. We can do some custom visibility queries, which will be accelerated by the GPU via the ray traced hardware module. We can implement a hybrid renderer, and we can do cinematic rendering. I mean, you tell me. So this is what I have. Thank you for listening to my talk.
Yes, thank you very much, Antonio. We have time for one question. If someone wants to ask a question, Antonio, yeah, here in the front.
I remember I was discussing this with Caggiano, and he was saying that if we want to do some ray traced effects like global illumination, we need to read the material information to get the material color. And for that, we will need binary rendering. Do you have any plans for implementing this in Godot?
Okay, so I attempted doing this, but it requires some time for me just to figure out where are the materials, where are they stored, how do I get them. So but at a certain point I stopped doing that because I didn't honestly have time to continue working on this from this perspective. And there is also another person which is looking into improving the interface of the ray tracing API. So I'm just waiting on how things will evolve, and then I'll jump in order to help and review, which is still something I still do. I still review PR which are going to touch the ray tracing API. So I guess it's a matter of time.
All right. Thank you for the talk.
Thank you
for listening,
again.
everybody.